Hi everyone, this is Andre again. In the last video I looked at the discrete logic, Commodore PET and the video output. So in this video I'm looking at the CRTC models, the 4032 and the 8032. Stay tuned. So while in the last video we have looked at the Commodore PET without the CRTC with discrete logic for video output, today we are going to look into these two models, the 4032 and the 8032, which have a CRTC video chip, and we'll have a look at how it works in principle, some demos and so on, including again a schematics deep dive if you stay on the video for long enough. But first we'll start with a recap of some of the things that we learned in the previous video. So previous video we looked at these two machines and we learned that in this block diagram how the hardware is structured to actually implement the video signal. We have all those counters and so on. We have address selector, video RAM, latch, character ROM, and so on. And this is all done to create this fixed timing that we have here on the video output. So we have 8 raster lines per character. We have 25 character lines. We have 32 character lines in total, plus some 4 extra raster lines to get the timing right. And so this is all 40 characters in a row and 64 characters total. And then we have some horizontal drive signal, vertical drive signal to control the video output, and that's all the fixed output. But what we can do with that, so we learned from this diagram, we have a fixed character ROM, and what we've seen is this vertical drive here is connected to an interrupt input on one of the I/O chips of the Commodore PET. So let's have a look at what we can do with that. So what we've learned is that the Commodore PET has a fixed character set that is in ROM and it cannot be modified. So let me show you how that character set looks like. And so you see here, this is the character set that is in ROM. It's only the upper half, it's 128 characters. And the second half, the other 128 characters, is inverted in hardware. So using all those characters, this is uppercase graphics mode. You can change that to lowercase, where some of the graphics characters go away. But this is uppercase graphics mode, and you can use these graphics characters to create boxes, RAMs, lines, and so on. So this cannot be modified, but this should not be possible, right? So this is a very smooth curve. It's an approximation of a sine wave that is moving over the screen. How is that possible? So what we've learned is the PET, and that is for all models. The one I've described in the last video with the discrete video output, as well as the models that I'm describing in this video with the CRTC chip, are reading all the character data for every raster line. So all the memory for these characters is read, for each character is read 8 times, because we have 8 raster lines per character. And that means you can raise the beam. The CPU can modify the value of the memory after every raster line has been read and displayed. And that is exactly what is happening here. So let me show you in in a program how that works. When we look at the timing diagram for the CRTC, this is from the Commodore 6545-1 documentation. We see that the vertical sync that is connected to the I/O chip to generate the interrupt is starting at a very defined place at the beginning of the raster line as defined in the CRTC register. And this is the fixed point we can use to start calculating the cycles from in the interrupt routine. So let's have a look at some of the calculations. So this RRQ to screen value is the number of cycles from when the vertical sync starts to where the actual first character starts on the screen. So we have the number of total character lines on screen minus the actual sync position. This is in terms of character lines, so we have to multiply that by the number of raster lines per character, and then we also have to add the vertical adjust, which is in raster lines, and then to get to the cycles, so we have, this is the number of raster lines between vertical sync and start of screen, and then we have to multiply that with the cycles per line to get to the actual number of cycles. Then there's some adjustment value, and that is the number of cycles that the kernel needs from going into the interrupt until it jumps to the interrupt routine via an indirect jump that we're going to have a look at in a moment. And then we can use this one to actually calculate the offset that we need to set the timer to when we get the vertical sync. We set the VIA timer to the raster line that is actually relevant for the effect. The effect line is defined here, which is 0. In this case, it's the start of screen. So basically, it's the IRQ to screen, and the other stuff is all 0. And then we take or subtract the adjustment that we need for the kernel routines, and this is the value we'll see below being used to set the VIA timer. So at the beginning, what we do is we set the interrupt vector of the PET kernel to our new interrupt routine. And then we have the new interrupt routine, and we look at if there is vertical sync interrupt. If not, we're going here. If yes, so let's have a look at that first. We set the timer 1 in the VIA to free running mode. We enable the timer 1 interrupt. We set the timer to a specific value, and this actually sets the latch and the timer, but you really want to start the timer with that value. And then we reload the latch of the VIA timer with the number of cycles per line -2, because the VIA timer counts the value it's set to +2. And the reason for that is this is the initial count that the timer counts, and when it underflows, it's being loaded again from the latch, and the latch now has another value, so that when we have that interrupt from this timer, after that the timer underflows every raster line, and that is an easy thing to check and see that we can stay in sync with the actual raster. Now let's have a look at the raster routine. In this here, the routine jumps into when the VIA timer fires, so that we had the vertical sync timer, and then we had this offset until to the raster line where the effect actually starts. We clear the interrupt flag, and then we actually have a number of those loops. I didn't do a full loop unrolling, but I have a loop for each character line, because in the character line this value stays the same. You can see here it's plus 40, it's plus 80, and so on. I wait for the timer 1 underflow, which means the raster line timer has underflown. I clear the flag. I set the value in that particular location. Then I increase x, which is the index in the sine wave data where it comes from, and I decrement a count which is actually preset to 8. So I have 8 loops in here that allow me to change that value every raster line, and then this goes on for I think 20 something lines that I implemented it here. You can see the value is increasing every time, and yeah, that's actually it. It's that simple. Now let's get to the actual topic of that video. So let's have a look at the CRTC models. Looking at the static pad or the dynamic pad with the discrete logic, I have marked all the parts in yellow that are now actually included in the CRTC, cathode ray tube controller chip. And you can see suddenly that the whole block diagram looks much more simple. So we have the CRTC that creates the addresses for the video RAM, for the video refresh. We have the CPU interface. We have an address selector that selects if the CRTC or the CPU addresses the video RAM. We have the latch that takes the data from the video RAM, or we have the feedback to the CPU for the data for the CPU access. We have the fixed character ROM. It's still fixed character ROM. The hold delay for the bit 7 for the inverse bit is still there. We have the shift register and inward out. So this is basically the same. So aside from this being a single chip that includes a lot of components that have been on discrete logic in the previous models, this also allows us to create a complete dynamic video timing. So you can see here all of the values here, the number of horizontal displayed characters, number of horizontal total characters, the horizontal sync position, or the width of the sync, or the number of total rows. Everything is determined by specific registers in the CRTC. So to get a display synced with the display output and showing the correct display output, you have to note some things. In general, the display will sync to a fixed number or a specific number of total horizontal characters, so that's a specific horizontal frequency, and it will also sync to a specific vertical frequency, and that depends actually on the on the region where you, so for example you have 50 Hertz regions, we have there we have 50 cycles per raster line and 400 raster lines to get a screen refresh vertical frequency of 20 milliseconds or 50 Hertz. For the 60 Hertz regions, it's different. So the NTSC timing, for example, is 64 cycles per raster line and 260 raster lines, I believe. So as long as you keep that overall timing, the machine should really sync to that signal. How is it positioned on the actual display? And that is the position of the horizontal sync and the vertical sync. Those are basically fixed to the screen positions. So you can see that here I've tried to overlay, feeble attempt, the sync positions. That is the vertical sync position, this is the horizontal sync position. Those are fixed in, basically tagged to the actual hardware on the screen, and the timing determines how the screen, the display, is positioned. As an example, what happens if you increase the vertical sync position or increase the horizontal sync position? Right, because these sync positions are fixed, the display of the actual characters moves to the left or up, because if you increase the time from start of screen to the sync position, you decrease the time on the other side between the sync position and the end of the screen, and the whole display that starts here at the beginning of the raster line moves to the left. And let's show that in a real demo. So if you want to access the CRTC registers, we have to use an indirect way. The CRTC only has 2 registers in the CPU memory map. It's a status register that you can read and an index register that you can write to, which are on the same address. So you cannot read the index register, but you can write it, and that is the actual register that determines the register that you can access with the second one, with the actual register content. And in the Commodore PET we have these 2 addresses, hex E880 or 59520 for the index register, and hex E881 or decimal 59521 for the data register. And you can simply poke the values to those addresses, and they will end up in the CRTC. For example, you can just use that. So I've just shown how we can change the registers in the CRTC chip. So, and I've also shown what should happen if we change the position of the horizontal sync or the vertical sync. So let me show you the horizontal sync first, which is register 2 of the CRTC chip, and then I can put in there, this is the default, is 41. Nothing happens because that's exactly how it should be. Now what happens if I increase that? Bang! And as I've shown in the slide, the screen moves to the left because I have moved the sync position in relative to the start of the screen more to the right. But the sync position is fixed here on the monitor, and therefore the whole screen moves to the right. You can go even further, or we can go the other direction. This could have been an alternative to fixing the position with the with the cutter tray tube itself, but this is basically fixed for all the machines at the same point. So let's look at the vertical sync, which is register 7. And when we go here and put in the default, which is 37, nothing happens. But we can also increase it, like I showed on the slide, and again the screen moved up because I've increased the distance between the start of screen and the vertical sync. The vertical sync is basically tacked to this bottom of the screen, so the whole screen, the start of screen moves up. And there are some you can also go down. Oh, sorry, the other direction. Yeah. And there's an interesting effect that you can do if you go lower and lower. You can do it like this. And if you go to this one, what you can see here, the screen is being displayed here on the bottom. And then in the 11th, I poked in 11th character line, there is a sync that's tagged here. And everything that's below the 11th character line after the vertical sync is drawn during the retrace and then starts up on here again. And I can actually cursor down, the cursor moves up during the retrace, goes there and some more, and there we are. And I can close the default again, put it in here. Nice effect, isn't it? So now that we've seen we can change those values in a static way, but we also have learned that we have the raster, the start of screen interrupt, and we can actually count down for a specific raster line and what happens if we do that in flight and then change it back. So this program waits until this raster line here, then changes the sync position, the horizontal sync position, then waits for 8 raster lines, 1 character line, and then switches it back. But you can see this is disturbed here. You can easily see when I just go down with the cursor, you can see the cursor is kind of messed up. You see, what you actually see here is, what we've done is we have changed the distance between the sync on one raster line, or the time between the sync on one raster line and the time of the sync on the other raster line. And the CRTC, the monitor tries to adapt to this. And this is an analog circuit, or at least somewhat mixed maybe. It tries to adapt, and then there is some wiggling basically when you do that. And the same thing happens when you move the horizontal sync back. Then of course it tries to wiggle back in the other direction. But we can do better than that. Now what this program does is, you can see it actually does a very nice moving of one character line, one position to the right. So if I go cursor down on the 4, it goes one position to the right as well. If I go cursor down again, it goes back under the 4 where it was before. So how did I do this? In the raster line before this character line, I increase the total number of cycles for that line by 1, so that the start of the next raster line for that, where the 5 is moved one further, is 1 cycle later. Then in that raster line I change the horizontal sync position so that it is basically in line with the other sync. So the monitor doesn't even notice that there has been any change. And the same happens when I leave that one. Before I leave, the raster line is made 1 cycle longer. Sorry, 1 cycle shorter again. And Thus, the next raster line starts one cycle early. And then when that raster line has started, I change the horizontal sync position again so that it's in line here, and then the monitor, the CRT actually does not know anything. So this is a way you can do a scroll of certain parts of the memory. You of course have to make sure that screen memory is adapted and filled with the right patterns and so on. But you can, this is a way you can scroll parts of the actual screen. One other thing that is interesting here is if you look at register 1, which is the number of displayed characters per line. The usual value is 40, and this is even the value for the 80 column machine. So, and I'll talk about that later, but you can increase that value as well. So what you see here is in the first character line, there's one character more that is being displayed, and it's taken from the next character line. Actually, this is not the very first one, because that's the second one. So this is coming from the bytes 3 value and so on. And every raster line is now 41 bytes. And the CRTC reads 41 bytes from memory. And the next line starts 41 bytes further, and not 40 like it is normally. The kernel does not know about this, so it's just doing its thing as if there were only 40 characters. But we can even go any further. So what's happening now? What you see here is you see these other, well, kind of characters which are very wide and are turned and are mirrored. So, and the reason for that is now we have so many characters that are being displayed. The display is going over the horizontal sync and it's going into the read trace. So if I move the cursor to the right, you can see here like how the cursor is underneath that ready prompt, which is basically seen here, and I can move one cursor up, one line up, and then you can see the cursor coming here. And because we only show 45 characters after the Y from the ready prompt, which you can see here, the dot is in the next line. That's why it's here. So I move to the right, not to the left, because this is mirrored, goes the other direction. And then you can, and this is what is called kind of mode 2, because you actually have more or less 3 colors. You have dark black, you have black, you have light green, and you have dark green, and you have bright green. And by cleverly setting the values in memory that are being shown here, you can create interesting effects. This is what's called mode 2, if I understand it correctly. But it's actually totally simple. Well, also what we see here is those machines only have limited memory for video. The size of the video memory is limited. The display is running out of memory because it's still displaying 25 lines, but now with 45 characters. So it's going over the 1024 bytes of character memory, and it starts again from start. So what you see here, this byte 3 appears here again. Byte, you see the retraced YTE, there's the S, and there's the 3. So for that reason, you have to make sure, if you're doing such effects on the CRTC, you have to make sure that your memory fits and your memory map of the video memory is being used properly, and so on. It's a very restricted set of features, but maybe that's a challenge people like. Another thing you can do with the timing is character height. So let me show you how that can work. So I've written a small program that adjusts the number of raster lines per character, but still keeps the overall video timing. So the number of total raster lines is kept constant even if you adjust the number of raster lines per character. So if I add plus, now we have 9 raster lines per character. If I add 10, this is actually the uppercase lowercase mode of the CRTC, because the of the PET, because the CRTC is programmed differently and it is set to 10 raster lines per character to give that line between the actual characters. That's spacing, sorry. And then you can see here, once the number of the characters are high enough, times 25 character lines, the number of raster lines to display goes into the area of the vertical retrace, and then you start seeing those artifacts because they are displayed on the vertical retrace. And you can, and this is basically the highest thing you can actually use. But you can also go lower than 8. Okay, 5 and 4. And then 4 is basically the minimum you can do with static timing, because if you go below 4, you would need to have more than 128 character lines to display the whole screen with 400 total raster lines, as is required by the screen geometry. But we can work around that as well. So this is again an interrupt-driven program. And you can see here, those raster lines have the normal height. And then suddenly we have a number of raster lines that have only 2 pixels high. And the reason why this is working is because not all of those character lines have that height. So that could be used for a graphics mode that is done by on a part of the screen, and the rest of the screen make sure that in the end I have actually added a number of displayed raster lines. So in the end we get into the 400 raster lines that this screen geometry requires. And then you can use like those graphics characters that you have on the keyboard here, for example, to create such small dots and do some drawing with them in that specific area of the screen. So let's look at how the CRTC actually works. And for this I have a little bit redrawn the picture I've showed before, where you have the CRTC and you have the different components that are being used in the video generation. So this is the 40-column PET, and this looks in principle very similar to what the original PET with their discrete video logic had. You have the address selector, VRAM latch, and so on, all those components. Now the question is, how did Commodore implement the 8032? And the point is, the 8032 was actually there before they had the 40-column, the 4032 CRTC models. So, but the problem is the video RAM still only has an access time or speed for 2 megahertz, which means when the CPU accesses the video RAM, you have half of the time for the CPU and half of the time for one video RAM access, so reading 1 byte. And we have, you know, we have 40 cycles per raster line, so we need to have those 40 bytes. And these exactly fit into the 1 megahertz timing of the CPU and of the system itself. So we cannot get more than those 40 bytes, but how do we do 80 columns? How do we get 80 bytes? And the solution that Commodore did is actually rather simple. They just doubled the bandwidth. They added a second video RAM chip, connected it to the appropriate buses, added data buffer and latch here, and this means that every time the video reads 1 byte from the video RAM, or let's say it reads 1 address from the video RAM, it actually gets 2 bytes. Both video RAM chips are accessed at the same time, both bytes are latched, and then they are shifted out, converted and shifted out one after the other. And this is how Commodore made the 80-column mode work, well, quite efficiently actually. And this is also the reason why even on the 80-column PET you have to configure them for 40 columns to be displayed. So let's have a look at how the timing actually works. And I'm trying to follow the clock 1 cycle here on the top of the screen, where I have marked in different colors the different accesses or video addresses that the CRTC is sending out. And this is when the clock 1, or which is basically for the purposes here the same as the phi 2 clock, phi 0 clock, phi 2 clock of the CPU. So in the first half cycle, when the clock is low, the CRTC has an access. When the clock is high, then the CPU has an access. If you want to go deeper into that, look into the 6502 datasheet, how that works. So then we look at the first access of the CRTC. So we have the CRTC puts out this single address to the video RAM. The address gets routed to both of the video RAM chips, and then we have 2 different bytes that are ending up in front of those latches. Those latches take their the value 1 at that moment when the clock goes from low to high, more or less. Deeper timing in the schematics deep dive if you're interested. So this is how the two bytes for the video are being read. And then we have the next half cycle where the CPU is accessing the video RAM. We have the CPU address, if it's addressing the video RAM, actually doesn't have to be all the time. Then depending on which address, if it's an even address or an odd address, the data buffers are being put on transparent, and the CPU can write and read those values. But the latches now have, because the clock has gone from low to high, they have the value, but only one of those is for now being set to output, and that's the even one, and this goes to the character ROM, and then we have the after some delay caused by the character ROM, we have the information about the pixel data in front of the shift register. And this one is loaded at the end of phi 2 and the end of phi 1 in phi 1 and phi 2. And that is every time the clock here changes. So when we go to the next phase, we can see that we have the new address for the video. We have another 2 bytes coming in that are ending up before the latches. The latches still have the old values. Now the odd latch is being set to output. This goes to the character ROM. While during the transition from CPU to CRTC, the shift register has taken this value, has loaded it into the shift register, and is now shifting out that data. What is interesting is we read the CRTC value I call CRTC 0 here, start reading it here, and we begin shifting it out here, one cycle after we shifted it, after we actually read it. The display enable signal of the CRTC starts here when the first address is being sent out from the CRTC, and that's why we have a certain delay circuitry here that delays the display enable output for one cycle in the 80 column case, so that the data is actually blanked out at the right time, and you can see all the colors, all the columns. Next CPU cycle, again we still have the second address here on the address selector, but the CPU is taking the bus. The latches have the values from the CRTC1, from the second access. Again, the even data is sent to the character ROM. But in the meantime, as we've seen here, the shift register has then taken the value from the pixel value from the character ROM from the previous one. You can see that on the color, and is shifting those out. So you can see that at here 0 odd. And then next cycle we have the third byte from the and so on. So this continues on, and this is basically how the timing at a very high level of the CRTC in the 80 column PET works. As a bonus, I can show you how the color PET works. The color PET is a system invented by Steve Gray, and there are some improvements from the community. And this is a way where you can extend your universal PET, which is the one board that can be used for 40 and 80 column PETs, for creating color output. And the point is, you're doing all the things with 40 column timing, but you still have the second video RAM and the data buffer and the latch installed. And you have to do some, the address select is of course here that this is the first kilobyte and this is the second kilobyte. It's not interleaved as 0, 1, 2, 3, 4, 5 and so on, odd and even, but this is separate blocks of memory then. You have the second latch, but this needs to be cut off from the data to the character ROM, but instead goes into another delay latch, because you have the character ROM is taking basically some time, and you have to put it in the shift register and so on. It's all delays that happen here, and then you take the output of the video, and then you select the upper half or the lower half of that byte from the second video color, and the 1/2 byte, the one nibble is the foreground color and one nibble is the background color, and then you take it and output it as RGBI. Very nice, very inventive, very cool thing. So let's look at the schematics in a real deep dive. The schematics are separated again across multiple sheets, and in some ways they are simpler because we have the CRTC. In some ways they are more complex because we have the 40 and the 80 column. What we should also not forget is that the 8032 was first, and that was a purely 80 column model, and then Commodore modified that board into what is called the so-called universal boards. I may have mentioned it before in that video. Those universal boards have the option to be used as a 40 column 4032 model or as an 80 column 8032 model. And they did this with a number of jumpers and parts options, where you can leave out a number of parts from the 8032 model, change some jumpers, and then you actually have a 40 column model. And in the meantime, there are even extension boards that can make that switchable. What we're going to do here now is we look at the original 8032 models, look at the schematics because they are a bit simpler, and then we look at what is different in the universal board. It's actually not that much. So let's look at the first sheet. We have the clock generation and DRAM controller and refresh address counter. We'll look at the clock generation first, and here we have the 16 megahertz clock that goes to various parts, and the first part here is a 4-bit counter that counts the 16 megahertz down to 8, 4, 2 and 1 megahertz. And this 1 megahertz is clock 1, is basically the system clock. It goes to phi 0 to the CPU, which is basically with a little delay it's phi 2. The 6502 main clock. We have an inverted not clock 1 here, and we have a delayed clock 1 here, which is used in various parts, but it's not that important for that matter. It's just basically all clock 1. Here we have the shift register load for, and remember this is the 80 column machine, so the pixel clock is 16 megahertz. You can see that up here, and here we have 8, 4 and 2 megahertz clocks, and they are all NANDed to create that shift register load signal, which means that this is at the end of every half cycle for the system clock. We'll see that in as I've shown it. Basically every time the system clock changes, we load the shift register, as we've seen in the timing diagram before. Clock 1 goes into the shift register here, that is clocked with the 16 megahertz clock again to create different phases, different delayed versions of the system clock, and 2 of them are being used to create this video RAM clock, which we're gonna have a look in a moment. The other stuff, DRAM control, is for the main memory, dynamic RAM, control lines, CAS, RAS. It's not important for this discussion. The refresh address counter is actually what was in the original PET, in the static PET, was the counter for the horizontal line, but this is not, of course, not used anymore because the CRTC is doing all that stuff, but it's still there because it's actually creating the refresh address for the dynamic RAM. Not in this video. So here are the changes on the universal board, the one board that you can configure between 40 and 80 columns. And we have here, there's one jumper where you can change the clock from 16 to 8 megahertz, 8 for the 40 column machine, 16 for the 80 column machine. This is the pixel clock. Pixels are only half as wide on the 80 column machine, so that's what happens here. Here we have the shift register load signal. The 4 MHz clock is not needed anymore here, but it's using instead the clock, an inverted version of the clock 1, and you can have a look at the detailed timing later, how that affects the shift register load. There's also a clock 2. I haven't found it actually on sheet 8, so maybe I missed it, but I don't think it's there. So those are the differences. So compared to the original to the earlier versions, this with the discrete logic, this has in a way it's still the same, because you need the refresh address counter, and you still have that shift register and so on. But the importance for the actual video circuit has decreased, because the address counter is not used in the video anymore. Then we have the video RAM address selector, which is where you have the select between the CPU and the video RAM addresses. So we have the bus address 1, 2, 3, 4, 5, and so on. For the from the CPU, and we have the TA0, TA1, and so on from the video chip. And you can see here there is a slight offset. The video chip has the address line 0 on this input 3, while the CPU has address line 1 on input 3, and those are switched against each other. And the reason for that is the video chip counts this address, but it reads both, as we've discussed, both bytes for the even and the odd addresses, while the CPU has basically 2 different addresses, and it's using BA0 on some other place, we'll see in a moment, to select between the odd and the even RAM chip. So that's why those addresses are shifted here. And that's for the 80 column model. And when we look at the universal PET, we see that we have all those jumpers. And now we can see in the 40 column we only have the even RAM chip and not an odd video RAM chip. So we have to move all the jumpers here off, so that TA0 is switched with BA0 for the 40 column machines, and BA1 for the 80 column machines, and so on. This is one of the most tedious things you need to do when you modify a board between 40 and 80 columns. So let's look at the core of the video generation. We have again a number of blocks here, so on. So let's have a look at these first. And this is basically the same as in the discrete logic versions. We have the RAM chips here, the even RAM. Those are 2 RAM chips. This is 1K by 4 bits. And this is where the switched address is coming from the previous sheet, and is going to these 2 chips. And we have the 8 output bits, and those output bits go to the latch that takes the data after the first half cycle before the CPU takes over the bus, and presents it to the character ROM. And then when the character ROM is done, it has the output on the input of the shift register, and then the shift register can load that to the further output. And those are the data buffers where the CPU can access the video RAM. The other stuff is more or less rather simple. You have the display enable delay, which is done by load shift register. The shift register load is here 2 cycles, and then you have the You have the inverse bit delay, which comes here from the RAM data bus 7, or from the latch. From the latch goes up here and is delayed. This is all in the block diagram, and then goes here to this XOR gate where the shift register output comes, and then it's synced with the main pixel clock again. Some more output stuff, more output control, and then it is actually output. This here is actually to sync the display enable again after it has been delayed here. This is synced to the 16 MHz clock, so it's in the same, basically the same clock domain as the pixel output, so we don't have any artifacts at the beginning of a character of the raster line or not. Then we have the read-write select logic. You see here, this is the video RAM clock, and this is an LS42. It's a decoder, and it creates the read odd, write odd, write even, and oops, somewhere there is the low write, low read. Yeah, here this one is the read even signal, where it controls the data bus drivers between the CPU data bus and the video data bus. So again, that's for the 80-column machine. It's looking at the universal boards. We have that difference in the pixel frequency here. We have here the enable signal, output enable for the even latch. In the 80-column machines, this depends on the clock. If the clock is low, even is set as output. If the clock is high, the odd latch is set as output. But the 40-column machines only have the even, so you have to enable that all the time. So that's why you can jump that to ground here. There are some changes here in the creation, and one thing here is that the video RAM clock is actually not used anymore. So it's just the CPU Phi2 clock. We can have a look at that in the detailed timing later. Now we have the odd stuff, and this is in the 80-column board and in the universal board for both of them, but that's the same schematic, but it's only used in the universal board if you have 80 columns, and that is because that's the odd video RAM. So those are the other two RAM chips, 1K by 4 bits, the odd latch, and here the odd data bus drivers. And finally, you have the CRTC, which is again the same in the 80 columns and the universal boards. And yeah, that's rather simple. It basically has the CRTC chip and then all just the connections that are here. Some interesting things to note is we have a light pen strobe, so we can actually use a light pen on the Commodore PET with the CRTC, because the CRTC knows exactly where the electron beam on the screen is, depending on some delay, but that you can compensate for that in the software. And when you put the light pen on the screen, it gets that signal when the pen is there, and the CRTC controller, the CRTC, can record the position of that of the video address. Basically, when the pen strobe, the light pen triggers, and with that you can localize where you put your light pen on the screen. It's like a touch display more or less, but yeah, in those days we didn't have touch screens, we had light pens. Here the raster line, I didn't mention that in the previous slide. This is input to the character ROM. Again, the upper raster lines are actually here to switch off the display. So that's also in the other one. But the rest is basically, there's some inverters for the vertical drive and horizontal drive. It depends on the screen you're actually using. So, and that actually concludes the schematic deep dive. So let's have a look at the detailed timing. So when we look at the timing, we have to look at these two chips here on the on this slide, where timing is generated from the 16 megahertz clock. We have that counter. We want to see how the load shift register signal is created, and we want to see how the virtual video RAM clock is created. When we look at the timing, I use a spreadsheet because I hope you can read that better than my scribbled hand diagrams. So we have the 16 megahertz clock here. White is 0, dark is 1, and you see here how this progresses. And then we have the LS177 counter, which is this IC here. It's UD3. I should have probably put it there. And you can see the output, it changes on the falling edge of clock 16, so you can see here how the counter output progresses. And then on the 8032 you have the load shift register, which is this NAND, so this 3-entry NAND of QA, QB and QC of that timer, and you can actually see that it's all three QA, B, C need to be 1. This is only here in this area for the load shift register to be 0. And this means the shift register is loaded, transparently loaded. It's a transparent load on that pixel shift register here in this in this time. And then you have the 16-bit clock, 16 megahertz clock, and then you can see when it's loaded, it loads actually bit 7 already, and then you have to you output the other bits here. And that's why there's one reason why you have to synchronize that with the 16 megahertz clock in the end again also. So there's the video latch. When is the data taken from the video RAM into the latch, and it's basically the same time, but it's only in that time when clock 1 here is at the end of the first half. It's not in the second half, because this first half of clock 1 is video access and the second half is CPU access, and you only latch either 8-bit or 16-bit during that. Or actually it's 8032, it's the 16-bit here in this time. Let's look at the shifting of the clock for the shift rate to generate the video RAM clock. And this is, as I think I've discussed it briefly in the previous video, this is a very cool way of creating signals depending on a single clock. You have one signal, you put it in a shift register that is clocked with a very high clock, and you get all those different phases of the original signal, and then you can just take your two more or less signals of those, connect them with some logic, and then you can basically get any kind of derived signal here very easily. So the video RAM clock is defined as this NAND of not Phi2B or Phi2G, which is very strange because this actually means that the CPU access only takes place in this interval. I haven't yet found out what exactly the reason for this is, because This means the CPU must have the data ready here already, because that's then where the RAM is taking over the data from the data bus, and that is quite early compared to the usual timing. Those vertical lines here are this is the first half of a cycle, this is the second half of a cycle. And actually they changed it in the universal board for then again for both the 40 and 80 columns, and just taking the bus phi2. It's a little bit delayed compared to the clock 1 because it goes through the CPU, but it is not relevant here in that discussion. So how does that look like when you look at that timing? Basically, we have the clock 1 over here on the top. You have the display enable signal, and that's now it's interesting to see how this is delayed. So when you look at this, you have the display enable signal. This is delayed by two registers that are clocked with different clocks. This is clock 1B, and this is shift register up, and you see this is basically in these two places. So we see that this is display enable is delayed for one cycle, and then we see on the first half of the phi2 clock the video RAM is accessing the CRTC is accessing the video RAM, so it's the video read access, and then we have the CPU access. In after the video access, the latches have taken the 2 bytes. Then we have the character ROM, which takes the 2 byte, the even byte, and then puts out the pixel data, takes the video data odd in the next half cycle, puts out the pixel data, and so on. So basically what we've seen in the overview timing. Looking at the 4032, the top half basically is the same. The load shift register is a little bit different. What we see here is because the 4 MHz clock is not included anymore, the signal is twice as wide as in the 80 column mode. However, it's not at the point where it's not in the second half of the clock 1 as opposed to the 8032. So it's only during one CPU cycle is only one shift register load. Interestingly, it's in the middle of a cycle, but that's how it is. And when we look at the timing again, we have clock 1, we have the display enable, and then now because of the load shift register up timing here, we see that display enable is actually delayed for 1.5 cycle, which also works out with the other video timing here. So because the first pixel output for the first character starts 1.5 cycle after the CRTC has started the video, the raster line. So if you have a model that you can switch between 40 and 80 columns with the same video timing values, the screen of the 40 column should actually 1/2 character or 180 column character shifted to the right. So to summarize, last video was the original discrete logic PETs. This video was these two PETs with the CRTCs, which included the 4032 model and the 8032 model, and the 8032 model in the original version, and the universal board that includes both options, 4032 and 8032. And what I guess will be the next one is the 8296, because that's a completely different machine again. So I hope you like it. Thanks for staying here this far into the video. and hope to see you next time. So how did I do this? In the raster line before I changed the horizontal sync, I shorten the raster line for one cycle. Then in the next raster line, so then in the timing, the beginning of the raster line is blah 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 blah.